Hi, in today's video we will discuss another supervised learning algorithm that is called as support vector machine. Support vector machine is one of the very powerful classification and regression algorithm. SVM basically covers binary classification types of problem. In today's video, we will discuss following terms such as hyperplane, margin, support vector, maximum margin hyperplane, soft margin, and kernel. So let us start with the definition of SVM. SVM is used for classification as well as for regression. The concept of surface is known here as hyperplane, which draws a boundary between data instances which are plotted in multi-dimensional space. Output prediction is one of the two classes. Here we construct n-dimensional hyperplane model and assign a future instance in one of the two possible output classes. So basically in SVM, the classification is done with the help of something called as hyperplane. Now SVM model is used to build which discriminate data instances which may belong to different classes. Working in a simple way, if your data is one-dimensional and say for example these are the data which is being given by a particular training set, the SVM is nothing but plotting a particular point in such a way that the data will be get separated in classes or in different groups very clearly. So we can draw a particular point over a single dimensional axis so that one group of elements or data instances which are similar belongs to one side. Likewise, if data is two-dimensional, our SVM is simply a drawing a line or a hyperplane. So in this case, you must mind that whether it is a point or it is a line, in SVM we refer to it as an hyperplane. So basically we make a hyperplane such that set of instances and another set of instances which are different from each other will get separated very well. So here as you can see this line is called as best hyperplane because it separates different kind of instances very clearly. So goal of SVM is only to find a plane which is we call it as a hyperplane which separates the instances on the basis of their classes. So new examples are then mapped into the same space and we can predict the based on which side of instance it falls. Say for example, next instance is this one. So we have to check whether it falls towards the left of this or towards the right. If it is falling towards the left, then this instance must be of this type. If my new instance is falling towards the right of this plane, then instance must be of another class type. So this is the simplest idea of SVM. Now there are possible solutions of for a given hyperplane. Say for example, if this is the given set of data, we can make a hyperplane such as this black line or we can make a hyperplane such as this yellow line. Or likewise we can have a hyperplane with like this blue line or like this red line. All these hyperplanes are actually separating our data clearly. So any of these planes or any of these lines are actually represented using an equation of line. An equation of line says that if data is two-dimensional, let me call dimension 1 as x1 and dimension 2 as x2. Then equation of line is given as a of x1 plus b of x2 minus c is equal to 0. So for this particular line, same equation will be there. For another line, same equation will be there. But the component or the coefficient a, b and c would be different for each of these lines. So here we can have a line as in hyperplane for a two-dimensional data, but that line can have different components of A, B and C, and depending upon these values of A, B, C, we can see the line is having at different place. Here our goal is not only to separate out the data, but we have to find the optimal hyperplane which clearly separates data, which is having data more separable as possible. So SVM is here to find something called as optimal solution, which maximize the distance between hyperplane, that is with respect to something called as vector points or difficult points or support vectors. And here we consider those points which are near to the hyperplane. That would be get considered. I'll tell you how. So here our only goal is to maximize something called as margin. Now, in order to understand what is margin, let us understand what is the hyperplane. Let us consider this is the hyperplane. We will draw two different parallel lines over each side. That means we will draw a parallel line which is above this and one which is below this, a parallel line to this line. And wherever that parallel line, this parallel line can be drawn at this stage or at this stage or at this distance or at this distance anywhere. But here mind that parallel line must get collide with over data instances. So the nearest data points to this line is this and this, and over another class we have this point and this point which are very distant or near. So any two parallel lines which are intersecting with our data points over each and every side, those things or those data instances are called as support vectors. So support vector is giving us something called as margin. Okay, so the distance between support vector over the one side to the distance of another support vector on the other side, and that complete distance is called as margin. And we have to increase or maximize this margin as maximum as possible. Now consider another hyperplane, that is this orange line, and any two parallel lines with respect to this orange line we have to find out support vectors, that means those data instances which are falling on either side. So as you can see there are only one support vector, but moreover the distance between these two margins or these two parallel lines will give you another distance or next margin. So this margin is narrow with respect to our first margin which is being given by this red hyperplane. So here we have two hyperplanes which is separating our data very well. That is the orange hyperplane and the red hyperplane. But out of two, the optimal hyperplane is the one which gives us the widest margin. So here we have to decide functionally, which is specifying our subset of training data that is called as support vectors. And in order to find these support vectors, we have to use something called as quadratic programming. So there are many possible hyperplanes, and challenge of SVM is to select a optimal hyperplane which is giving us the maximum margin. Now this challenge might be very simple to understand in terms of 2D, but if data is three-dimensional or more, or I would say multi-dimensional, our hyperplane would look like a surface. So this, as you can see over the left hand side diagram, it is a three-dimensional data. This is my x1 plane, this is an x2, this is an x2 plane, and this particular axis is x3. So data is spread across three dimension and your hyperplane is a surface, and which is separating. Again, we can have multiple surfaces so that the data instances can be separated. But remember, challenge is again same. We have to find optimal surface or optimal hyperplane such that we have the largest margin or maximum margin which gives us a support vector. So here the generalization error in terms of SVM is nothing but measure of how accurately and precisely this hyperplane model can predict the value of previously unseen data. Now look into the formal definition of support vector. Support vector is nothing but a data point which are also very critical component in a data set which are nearly identified to the lines which is a hyperplane over the line which is a hyperplane. So let me call this decision boundary. Let me call this decision boundary is my hyperplane, and any two parallel lines which intersects with data point on either side is called as support vector. Now these support vectors are very important because if these data points are removed, then it might change the margin, because If this point is not present, say for example, our decision boundary would be changed. So if support vectors are removed, they will alter the position of dividing hyperplane. So we always make sure that whatever the hyperplane position or decision boundary is there, it is in the middle of left and right margin. So these two parallel lines are equidistant from towards the left and right of decision boundary. That must be get noted. Next, hyperplane and margin. For n-dimensional feature space, a hyperplane is n-1 subspace which separates our data or a classifies the data. As I said, if data is one-dimensional, we have only one point. If data is two-dimensional, hyperplane is a line. And if data is three-dimensional, like this way, then our hyperplane is a surface. So as you can see, if feature space is 2D, hyperplane is 1D, that is a line. If feature space is 3D, hyperplane is a surface, which is a 2D. So any data which is having more than 3 dimension is very difficult to understand, but we can conclude that for n-dimensional data, our hyperplane is n-1 subspace which separates our training data. So as you can see, this is a three-dimensional data and our hyperplane is a surface. Now let us look into the concept of maximum margin. Now what is the maximum margin? So first let us understand this diagram, this particular two-dimensional space. This is x1 and this is x2. These red points are of belonging to class 1 and these are the blue points which belongs to class 2. And we draw a particular decision boundary, or this is the optimal hyperplane I would say, and in order to calculate margin we have to find out two parallel lines such that we can find a support vector. So this is the support vector from this class and there are two support vectors from another class. As you can see, the distance between this from this support vector to the margin to the hyperplane and another support vector to the hyperplane is same. So here we call or we draw one vector which is called as W, and this vector is perpendicular to our hyperplane. Okay, so vector W is passing through origin and which is perpendicular to the direction of our hyperplane. So I would call W is a decision hyperplane which is a normal vector, and xi is nothing but a data point I. So any point which is here we consider it as an xi point, which is an ith point. So and yi is nothing but a class of a data point. Now here you must consider that class is not 0 and 1. Do not consider it as binary, but classes are considered as plus 1 and minus 1. Say for example, these are the plus 1 classes, that is one of the type class, and these are the minus 1 classes, for example. And we call or we draw a model or a classifier as f of xi, that is the functional mapping of any data point is nothing but a sign with respect to a given line. Now remember, this line is given as vector w xi plus b, where this is nothing but a slope and this is nothing but a y-intercept. So this is nothing but an equation of a line. So if any point x, say for example this is a point x, if it is falling towards the left of line, then it would have, if I substitute its value in this equation, this will be greater than 1 or it will give me value 1 plus 1. So I would consider it as belonging it to this particular class. And let me consider if this point is my question point, that is it, this is in my x class. I would substitute this x value into this equation, and if I get any value which is lesser than minus 1 or minus 1, I would conclude it falls into another class which is equals to minus 1. So basically, any function f of x I is nothing but given by a sign which is given with respect to an equation of an hyperplane. So sign of wt, which is nothing but a transpose of vector, is multiplied with a data point vector, that is vector multiplied by vector, plus b, which is nothing but a y-intercept. So functional margin, that is nothing but these two parallel lines, are given by y of I. This y of I can be plus 1 or it can be minus 1 into an equation of a line, which is nothing but wt into x of I plus b. Here you must note that in order to increase this distance, we must increase or we must change the value of W and B. So by changing the value of W and B, we can change the slope of a line as well as y-intercept, and hence we can change the margin of a line. We can increase and decrease respectively. So by increasing the value of W and B, we can do simple scaling. And that's why the functional margin of a data set, we can see it is a twice as the minimum functional margin for any point. So this particular thing is called as minimum functional margin. Likewise, this is also minimum functional margin. Hence, my complete functional margin rho is this. Rho is given as 2 times our minimum functional margin. So as you can see, factor of 2 comes in while measuring the whole width of a margin. So we say that the examples which are closest to hyperplane are support vectors, and the wider the support vector is, the wider the maximum margin, minimum margin is. Hence, if we twice that margin, we will have maximum margin rho in a given hyperplane. So here as you can see that this particular hyperplane is given as W transpose X plus B is equal to 0. Say for example this is an equation of line. So all those values W transpose B plus W transpose X plus B which are greater than 0 is nothing but this complete region, and all points which will satisfy to this equation W transpose X plus B greater than 0 is nothing but a region towards the right. Say for example, because every point data point over here, if substitute its x1 and y1 value over here, it will give me value 0. And if I substitute any data point which falls above this region, will give me value greater than 0. And any data point value in this equation, if substituted, will give me value lesser than 0, will fall over the another region. That's why we say that vector w into xi plus b greater than or is equal to 1 is belonging to our class 1. That is nothing but this particular region. Now you can see that here I am saying it is greater than 0 and lesser than 0, but in this equation it is I am specifying the values 1, because here I am not considering all the region which are with respect to this line. I am considering only region with respect to this margin. Why this margin? Because here we have concept of support vector. So I am expecting no points will fall inside this margin anytime. So all training examples are always above this particular line. So if this line is W transpose X plus B equals to 0, I can consider this line to be W transpose X plus B is equal to 1, and this line to be W transpose X plus B is equal to minus 1, because it is towards the another side. As simple as that. So any region which is above this must be greater than 1, and any region which is lesser than this must be lesser than minus 1. That's why we say W vector into X of I plus B is lesser than or equals to minus 1 belongs to another class, that is Y of I label is minus 1. And here for support vectors, we make use of inequality becomes equality. That means for this particular data point, it will be not greater than 1, but it will be is equal to 1. And for these two support vector, an equation of line will be not lesser than or equals to minus 1, but it will be only minus 1. That is what we are saying, that support vectors, which inequality, we are considering this inequality will become equality. And we say that the margin is nothing but 2 divided by vector W. So our margin, which is nothing but 2 divided by vector, this must get maximized. This component has to be maximized. We must say that reverse way. That means instead of 2, let me write 1 by 2, and instead of 1 by W vector, let me write this vector. If this component has to be maximized, I would say this component has to be minimized. So we have to minimize 1 by 2 into W vector in any case in order to get maximum margin. So let us summarize our working of SVM. This is the plane or a hyperplane. which is nothing but our optimal classifier, which is represented by a line W transpose X plus B is equal to 0. Towards the left, there is one margin which is giving a support vector, which is nothing but satisfying to an equation W transpose X of B plus B equal to -1, and towards the right margin all elements or all support vectors will have or satisfy this particular equation. Now for rest of these points we can write equation as W transpose into those data of another type B type will be lesser than give us value lesser than this, because any value towards the left of this equation will give us a value which is lesser than -1, and every value which is towards the right of another margin will give a value which is greater than this. For all these data points of type XA, I would write as W transpose into X of A type data points plus B will give us a value greater than 1. So in this case, our maximum margin is nothing but the distance between these two planes. The plane this one and the plane this one. So this is the maximum margin rho. Now let us see how classification is done of an unknown data point. So if we are given a new point x anywhere and we can score its projection onto a hyperplane normal and we compute its score with respect to this equation. Okay, and we will decide whether it is greater than 0 or lesser than 0 and compare its value to some threshold t. So let us say this is an equation of WTX plus B, okay, and is equals to 0, and this is the WTX plus B is equal to 1, and this is WTX plus B is equal to -1. Say for example there is a point x which is having some x1, x2 up to n dimension, or I would say this is the 2D plane that my new x point is having these two values. So whatever vector Wt component, so if we have found this plane, we must have component what is W and what is component B. So that Wt is multiplied with this x. So here in place of x, I would write it as Wt multiplied with x1 into x2, which are nothing but two dimension of a new x point, plus b. Whatever the component value or the value you will get, you will equate that a term with threshold, and that threshold, if it is positive threshold, we say it is belonging to class 1. If it is a negative threshold, we will say it belongs to class -1, that is this one. Else if that point is falling in between, say for example here, we will say we do not know the label of that class. All this discussion that we have done till now is called as hard margin SVM classification. Now let us look into soft margin classification, or where soft margin comes into the picture. Not every time our data is very well separatable linearly. So there are something called as non-linear data, or there is something called as misclassification or noise in our given training data set. That's why we add something called as slack variable, which is nothing but a calculation of soft margin. Here in SVM, we allow some errors, or which are the points which might belong to one class and classified as another class being calculated with some reasonable cost. Say for example, this is our data points. As you can see, if I draw a hyperplane at this particular range. Okay, so support vector of this red class is this one, and support vector of blue classes are these two, and complete margin is nothing but this row which is given, but as you can see there is one blue point here and red point which is falling on blue side, so we have some kind of error in our classification. So if we try to linearly classify this data, so no as such linear line is possible, linear hyperplane is possible which can separate this kind of data, so these two can be considered as an error, and the distance from our hyperplane to this is calculated and called as slack variable. So we have in total two different slacks. Towards the left of the margin, we calculate the wrongly classified red point. So support vector is this red point, and from this support vector we calculate distance to red misclassified point, and that is called as slack 1. Likewise, we have blue support vector points. This is nothing but another margin. From that margin, we calculate wrongly classified blue sample distance, and that distance is called as slack variable 2. So as you know, our goal of SVM is to minimize only 1 by 2 W vector that we have already seen, but we have to in SVM also minimize the summation of these slack vectors. These are nothing but an error. So error must get reduced along with this maximum margin hyperplane. So at some cost, the summation of slack variable, the complete term, we have to minimize for all set of data points given in a training example. So this is here we are trying to minimize the errors in a hyperplane which are far from their actual class or a large margin. So this is how we have seen, this is the classification or working of SVM when your data is of linear type. Let us discuss non-linear data. So as you can see, one-dimensional data is there and it is linearly separable. That means if we put our SVM or hyperplane here, we get two different support vectors at each with the same length, and here we can say the hyperplane is correctly fit or correctly finding the classification. But if data is given in this kind of scenario, in this scenario as you can see, either I put my hyperplane this side, it will misclassify these many data points. If I put my hyperplane at this side, this might get disclassify or misclassify other data points. So it is not possible to linearly classify these kind of data points. In these kind of cases, SVM do higher dimensional space. It transforms your lower dimensional data into higher dimensional space. So in order by say for example this is 0 and these are the negative numbers towards here and these are the positive numbers. If we take square, so square of a larger number will be larger, smaller number will be smaller irrespective of their positive or negative sign. So by taking square of this particular attribute, we add another more dimension and our data is later on classified. Okay. And later on, if data is in some certain kind of pattern, we can easily find out a linear hyperplane with some narrow margin maybe, and which can give us two different support vectors, and later on we can classify any type of data with the respect to this. So this is the method of SVM to classify non-linear data. It does or it transforms your lower dimensional data into hyperdimension and later on finds the hyperplane, and whenever the new point comes in, it first transforms that point into higher dimension and later on it classifies it. So here as you can see, this is the two-dimensional data. Here no such a line can be placed, a single line cannot be placed so that it can classify blue and red samples. So what do we do? Instead of two dimension, we add third dimension, and such that red samples and blue samples are now separated, and they are later on separated using a hyperplane which is denoted by a surface. So basically here original features are mapped into a hybrid higher dimension of our training data set. Here something called as kernel trick is used, because even though we can see that data is transformed from lower dimension to higher dimension, but in reality we do not actually convert each data point into higher dimension. It only calculates with the help of trick that is called as kernel trick. So kernel trick is a trick to find out the hyperplane in higher dimension without converting your data into higher dimension. So first kernel trick is something called as linear classifier, which is in which we have two data points xi and xj are actually taking vector product. So vectors cannot be classified or multiplied directly. In order to take vector product, we first take transform of first and secondly second vector is multiplied within it. So this is something called as mapping function of kernel trick, which transforms your X data into with the help of some transformation function. and this can be represented in an equation form as k of xi comma xj is equal to function of xi transpose into function of xj. Here in linear trick, we simply write this function as xi is taken transpose into vector product of xj. As simple as that in a form of linear. There do exist another function, kernel function, which may apply different operations over xi and xj and transform data into some different way. Let us look into different kernel functions. So as I said, kernel function is a form or is a method to find a hyperplane in a higher dimension without actually transforming data into higher dimensional space. We also have something called as polynomial function, and that polynomial function, any point or any data set is transformed. Xi and xj data points are transformed with the help of formula 1 plus x of I transpose into xj raised to p. In case of transforming data from 1 to 2 dimensional, this p will be 2. In case of transforming data from 2 to 3 dimensional, this will be 3. So p is nothing but degree or dimension of a new polynomial type. We also have some different or complex type of function which are called as RBF function or radial basis or Gaussian function, which is transforming your data points xi and xj into a form of e raised to minus x of I minus x of j square divided by 2 sigma square. Here, the dimensions that are used is infinite. As I said, here p can be 2, 3, 4, any polynomial value, it would generate an equation kind of. But here, the dimension in RBF are generated infinite, hence it is very difficult to visualize. But here, points are mapped in a such a way that it is easier to fit a hyperplane which can linearly differentiate or linearly separates binomial classifications or binomial class data points. High dimension space still has intrinsic dimensionality d, but linear separator is in correspondent to nonlinear separator original. SVM is very popular in terms of binary classification as well as in regression. It can handle both type of prediction problems very well. And along with kernel function, the performance of SVM is very good. The only challenge in SVM is to select the correct kernel function and different parameters of kernel that is needed to be set. But altogether, all SEM works very well for majority of classification and prediction regression problems. That is all for today. We have covered SVM along with its major definitions such as hyperplanes, margin, support vector, maximum margin hyperplane, soft margin and kernel. Thank you everyone for watching this video. This is Munira Topia signing off.